So hi everyone, welcome back to the DSC Tech Talk series. I hope you're all safe and happy back home with your loved ones. So I'm Amrita, I'm the lead for DSC University of Malaya. So I guess most of you now know about DSC, but for those of you who are joining us for the first time, Delta Student Clubs are university-based community groups for students who are passionate about solving problems and exploring new technologies. So it welcomes students from all undergraduate and graduate programs with an interest in growing as a developer. And our mission is just to help students bridge the gap between theory and practice. So what's great about being part of this community is that students get the opportunity to learn about the latest technologies and connect with people all across the globe. And for today's Tech Talk session, we have an amazing speaker who will be introducing a couple of dimensionality reduction techniques, namely PCA and linear discriminant analysis, which are respectively unsupervised and supervised dimensionality reduction techniques. So he'll also be demonstrating the concepts, share examples of how they're used, and go over the mathematics behind how they work. So before we bring in our speaker, let me just briefly introduce him. So our speaker today is Dr. Divyanshu Murli. Recently, he finished his PhD in theoretical physics from Stanford, and he spent the latter year and a half acquiring skills in data science and machine learning. So currently, he works as a data scientist at Kount, headquartered in Boise, Idaho. And Kount is a software company that protects digital innovations for 6,500 global brands. Our speaker applies data science and machine learning techniques to improve online payment fraud detection. So without further ado, let's welcome Divyanshu.
Thank you, Amrita, for the introduction.
Hey, so thanks for joining us today.
Yeah, I'm happy to be here.
So before we start with your talk, I think that many of our viewers here, they have many questions going on because like ever since we shared about your talk, I've been getting a lot of messages from students asking a couple of questions. So I'll probably first start with what really do you find is the most enjoyable thing about being a data scientist?
Yeah, that's a good question because 2 years ago, I guess 2 years and change ago, I didn't really know what a data scientist was. My background, as you said, is in theoretical physics, and really theoretical physics is kind of mathematics applied to natural phenomena, and so as such, it's very quantitative in nature. I got interested in data science and machine learning because it provided a way of systematically studying data. And in the world we live in today, with all the companies we have, with the sort of wealth of information we have on the internet, data is really at the center of everything. And being able to apply my sort of background to these sort of real world phenomena, these real world kind of data sets to improve to improve sort of model prediction or fraud detection or many other things, I felt like I was pretty suited with my background to sort of move into this field in industry.
Mm-hmm. That's interesting. And what skills do you think are important to be a data scientist? Because you shared with us that you spent like a year and a half acquiring skills for being a data scientist, like in machine learning and data science. So what would you suggest is important?
Sure. So I'll talk about that briefly right now, and I also have a slide at the end of my talk which will kind of go over this in more detail. But again, for me, coming from theoretical physics, I hadn't really done programming seriously before, like I'd say the beginning of 2018, and so it was a pretty steep learning curve because I had to like learn how to program in Python, learn basic CS fundamentals like data structures and algorithms, and on top of that, learn machine learning algorithms. So I think that generally, kind of coming from any highly quantitative background is a plus, because that already puts you way ahead of the curve and gives you that sort of mathematical foundation you need to understand how data science and machine learning work. And I'll go into that in more detail at the end on like what specific things you need. And also just kind of getting really comfortable with Python, because that's kind of the language of data science and machine learning, because all the main packages people use, all the libraries, etc., are all in Python. So just getting really good at Python, getting really good at some at the sort of mathematical foundation, playing around with data sets on Kaggle or other places, taking classes in machine learning. These sorts of things will all help in gearing yourself to go in that direction.
Mm-hmm. And I mean, earlier we were talking about your journey. I think that's really inspiring. You should probably share that with our viewers. Like you mentioned that you've done your PhD in theoretical physics, and now you're a data scientist, and you're so young. Yeah. So why don't you share with our viewers your journey to this?
Like how far back?
Just like what you told me earlier.
Okay. Sure. So well, okay. I guess I'll go back further in that case. I got really interested. I've always kind of had a very mathematical and quantitative mindset from going back as far as I can remember. I remember the first time when I was in third grade or whatever, when kind of I was sort of formally introduced to mathematics as a subject. I kind of developed this immediate affinity to it. Unlike anything else, like up until that point, I remember like everything was focused on language and kind of English and you know, more fuzzy things, I guess, for lack of a better description. But when I got to like third grade, when I was like 9 or 10, I was like, like mathematics was really kind of the thing that sort of came into my life, and that really almost changed my life at that point, because I sort of immediately, like, I felt like very connected to it. And from there, I think going from mathematics to physics wasn't really too much of a jump, because physics itself is innately very mathematical, but physics is also kind of grounded in reality. And that's kind of how I made the jump from mathematics to physics. And I went on, you know, the 9-year journey of college and grad school, 4 years of college, 5 years of grad school, you know, both in physics. And I wanted to stay as close to mathematics as possible while being in physics. So theoretical physics was kind of the perfect balance between, you know, doing, you know, really solid mathematics while also having some grounding in reality. And from there, I think I was drawn to machine learning as a subject because, like machine learning, like physics, machine learning is based on models, and physics, to sort of understand any particular phenomena, you know, like how, like my PhD was on using topics like aspects of string theory to applying aspects of string theory to the early universe and early universe cosmology. And what we did was we developed these models of early universe cosmology and sort of analyzed how those models worked. And in some sense, kind of physics sort of distills really complex phenomena to their essence by sort of, you know, making some, you know, simplifying assumptions, developing a model based on that, and, you know, analyzing that model. And as you sort of add more and more complexity, you know, you sort of increase the complexity of your model in some sense. And I think I saw many parallels between that sort of way to understand physics in terms of models in machine learning. And so I also, you know, I got, you know, so I sort of was naturally drawn to machine learning from that perspective. And you know, data science is kind of, I would say, it was some sort of a wrapper for machine learning. Data science is broader than machine learning, but I think machine learning lies at the core of what data science really is. And that kind of, you know, that sort of second jump, first from mathematics to physics and from physics to machine learning, was kind of a similar kind of thing of also wanting to sort of, at my core, use my sort of core mathematical knowledge and affinity and apply it to sort of, I guess, natural phenomena in some sense, not really like sort of natural and sort of physical phenomena, but sort of, you know, phenomena in the real world.
Thanks for sharing that with us.
Yeah, absolutely.
So I guess I'll be signing off now. So to our viewers here, feel free to ask any questions on the live chat. We'll be answering your question towards the end of the talk. And yeah, that's about it. So let me just leave the call.
Okay, so now I'm going to be talking about dimensionality reduction. I changed the title slightly, just because I thought it was more suited to what I'll be, the content of my presentation. So without further ado, let's get right into it. There we go. This is just a quick outline of what I'll be talking about. First, I'll introduce the concepts of what dimensionality reduction and the related idea of feature reduction is, and I'll motivate, you know, why we care about dimensionality reduction in data science and machine learning. And after that, I'll go into kind of the sort of mathematical basis for what PCA, principal component analysis, is, and how it works. It's based on this thing called the singular value decomposition, which you may have encountered in your linear algebra course. But I'll be kind of going into a little bit more detail about how it works and sort of motivating it from a data science and machine learning perspective. So I'll talk about the math behind the SVD, singular value decomposition, and I'll give an application to image compression. And I'll show how principal component analysis is really just a statistical kind of wrapper around the SVD. So the SVD is really at the core of what PCA is. PCA kind of can be used to elucidate the structure, the sort of underlying structure of a data set. And in particular, it can kind of give clarity into like how things cluster, if there are disconnected components, and so on and so forth. PCA, however, is an unsupervised learning technique, whilst LDA, linear discriminant analysis, is a supervised dimensionality reduction technique. And both of these kind of, are good at what they're meant for, but in the case where we have class labels, LDA might be the better solution. So I'll kind of do give an example of a head-to-head competition between PCA and LDA. And at the end, I'll give some concluding comments, and I'll talk a little bit about what Amrita had asked in the introduction about, some resources you might want to, some things you might want to know and brush up on to pursue a career in this direction. So I'm gonna kind of lay out the convention of this presentation of kind of how we'll be, what kind of data sets we'll be looking at. The type of data sets are these kind of tabular data sets. Namely, you have some number of features, and so this can be treated like this this row can be treated as a random variable, and where the length of the random variable is the number of features, and you sample from some distribution that's really data at its core is samples from some probability distribution, right? And you're trying to understand what that probability distribution is, and that's kind of what statistical learning is, which is where kind of machine learning originated. And so we have some set of features, and we draw samples, and this kind of forms this data matrix, and this is the sort of tabular convention that we'll be looking at, and I'll give examples of what these are, like what this might look like later on down in this presentation. So as I said earlier, we'll kind of motivate why we care, and the biggest reason for caring about dimensionality reduction is to explore high dimensional data sets. It can be very difficult to understand the underlying structure of a data set, especially if it's high dimensional. And by high dimensional, I mean it has a large number of features. So in this slide here, the number of features can be very large, and we may not know what the structure is. Like maybe in this particular data set, like a certain set of points might cluster in one part, and a certain set of points might cluster in another part. In this very high dimensional, maybe 50-dimensional space, and just by looking at the data, it's hard to see that. And so PCA particularly allows one to distill a data set to its essence by choosing the sort of salient features. And I say Eigen features here because of the way PCA works, and I'll go more into that later on. I think most commonly people use PCA for visualization. Sort of if you want to understand like clustering, for example, PCA is the kind of your best friend, because you can kind of find the sort of main, project the data set onto the sort of the main directions. And I'm being deliberately vague about main here because I'm going to talk very explicitly about what main really means. But if you can imagine, there are some directions that are the important directions, and there are other directions which are less important. And if we can just retain those important directions and project our data down onto those important directions, then maybe that can give us some further insight into what this data really looks like. And I would say that sort of PCA and the content of this talk is really a way of understanding the essence of the data itself, and not preparing it in some particular way to feed into a model. So that's something that I'll talk about, but I just kind of wanted to preface that. Before I kind of go into the main meat of the talk, I kind of wanted to go over some primary methods for dimensionality reduction and its closely related cousin feature reduction. I think if you go online, I was just kind of reading on some blogs, people kind of clump these two things together. I would say they're related, but they're not exactly the same thing. So a couple of examples of feature reduction are, let's say that we have, in machine learning, we're training some model. It could be a neural network. It could be like just a simple logistic regression. It could be a random forest. It could be some other really complicated thing. Maybe we have some data set that we feed through this model, and it has some insanely large number of features, and most of them aren't particularly relevant to model performance. So one thing you can do is take your large feature set and kind of remove one feature at a time, and check model performance. And if you sort of run across a feature like such that when you remove it, the model performance drastically drops, and you'll say, okay, well, that's actually a pretty important feature. I probably shouldn't get rid of it. But in the case where maybe like removing the feature like either negligibly sort of hurts model performance, or maybe even improves it, because there are like sometimes you can have so many features in your data set that your model gets confused and doesn't really know what to say. So kind of removing the sort of crappy features from your data set, in fact, in some cases, could improve model performance. Another technique is to use a random forest, because a random forest, like the way it works on a high level, is that it's a bunch of decision trees, and a decision tree is kind of like a flowchart in some sense. If I feed in a feature, and I might say, okay, split on, I'm trying to, like, let's say, as some examples, like let's say, like I'm trying to predict, the probability that a student gets into college based on their exam scores, their grades, the amount of outreach they do, etc. And you can kind of codify this in some vector. And the decision tree will say, like, okay, well, if the student got X number of failing grades, then go this way, otherwise go the other way. And you can have that for each feature, and then at the end it'll be like an answer that says either they did it or they didn't do it. And a random forest is like a way of aggregating a bunch of decision trees. It turns out to be like a pretty solid machine learning algorithm, even though it's a pretty simple one at its core. So the way that sort of the feature reduction, sort of feature importance is calculated is via this thing called information gain and/or Gini impurity or /purity. I won't go into details of how that works, but like this is another way in which you can kind of select important features by sort of feeding it through your model and outputting some set of important features from the most important to least important, and you can kind of just lop off the least important ones. So I just wanted to go over that to sort of distinguish between what feature reduction is and what dimensionality reduction is. And in this talk, I'm going to be focusing on dimensionality reduction as opposed to feature reduction. Feature reduction is usually done to sort of find the most important features, say, for a particular model. Let's say, like in this case, like if I have some neural network and I want to find the most important features to maximize, sort of optimize performance of this neural network algorithm. Or maybe I have a bunch of maybe I have a bunch of features, and I just want to understand like which ones are important, which ones aren't, because like just by looking at them, I don't really know. But in contrast with dimensionality reduction, it's really a way of looking at the core structure of the data itself, looking at like what does it look like, what's it shaped like, how many distinct clusters are there. So I think dimensionality reduction is really like a model independent technique to understand the real core of the data itself, and understand like what the data really looks like. And there are kind of two main, I would say, techniques used. Like the most common one is PCA, principal component analysis. And that's kind of what I'll be talking about in the bulk of my talk. But another one, which is also pretty useful, is linear discriminant analysis, because it also makes use of class labels and tries to sort of maximize the separation between classes. Incidentally, linear discriminant analysis is also a classification algorithm in addition to being used for dimensionality reduction, while PCA is really just a dimensionality reduction method. Okay, so I've sort of said a bunch of things, but now let's kind of put this on paper and kind of look at it more concretely. Let's say we have some toy data. This is just some abstract. I just took some the way I generated this plot was I took the line, the sort of y equals x line, and I sort of added some Gaussian noise to it. And you can kind of see that in this case, pretending that this is real data, like there's a very, very strong correlation along this 45-degree line. And there is like some stuff that goes up and down, but like we can kind of describe the data by projecting it onto this red line right here. And this other red line, this orthogonal red line, is a sort of other direction in which the data kind of varies. And this is kind of what I mean by sort of understanding the underlying structure of the data. You can imagine sort of this data is two-dimensional. You can imagine if I were to project it onto this one-dimensional submanifold, or this one-dimensional surface, then I wouldn't really lose a whole lot of information. I would pretty much mostly retain the structure of the data. Sure, I would lose sort of the vertical variability, but assuming that it's much smaller than the other, the main diagonal variability, then I wouldn't really lose a whole lot, and I can capture this two-dimensional data in one dimension. And that's kind of what dimensionality reduction is. I'm reducing the number of dimensions in my data set, i.e. I'm projecting it from a higher dimensional space to a lower dimensional space. And that's really what PCA seeks to do. So like I said, we just had two dimensions here. We could very easily say, look at this, there's very strong correlation along x and y. So this is the direction of most largest variability. Now, of course, if we have a whole bunch of features, 100, 1,000, 1,000,000, and what have you, million's a bit much, I'll grant you that. But if we have like a lot, really, then we can't visualize that. We live in a three-dimensional world. Like maybe if it were three-dimensional, we can look at it in 3 dimensions. But if it's more than that, then we're kind of out of luck. So that's why PCA is super helpful for visualizing very high dimensional data. So now I've sort of told you what PCA is good for. I'd like to go into the core of how it works, because I personally think it's pretty interesting. It's based on this thing called the singular value decomposition. The singular value decomposition is really a technique for decomposing a matrix into these 3 pieces here. So just to go into some more detail, we will kind of introduce it from a linear algebra perspective of sort of diagonalizing a square matrix. You've probably seen before that, you can take any square matrix, not any actually, most square matrices, and sort of decompose them into their eigenvectors and their eigenvalues. And sort of in this sort of change of basis, I can take a matrix in some random basis and then go to its what's called eigenbases, which are these sort of special. This is a special basis, assuming that the sort of the eigenbasis does span the entire space, and that's the case certainly for all the data, for all the matrices we will study here. There are edge cases, but we won't have to worry about them for the purposes of this talk. If we sort of go into this basis here of eigenvectors, then the matrix itself in that basis is just a diagonal matrix. And so diagonal matrices are a lot nicer and simpler than any other matrix. And so we generally tend to like diagonal matrices. But this is great, all well and good, but most data isn't square. Most matrices aren't square for that matter. So, how do we generalize this notion? Turns out that it is possible to generalize this notion of diagonalizability to non-square matrices via the SVD. And I won't go into why this is true, but it is true, and it can be shown that any matrix, any rectangular matrix, can be written. And I will assume that it's real for the purposes of this discussion, because data is real. Any rectangular matrix can be written in this form, decomposed in this form, namely a sort of a diagonal-ish matrix that is sandwiched by orthogonal matrices. And by orthogonal, I just mean that the transpose of the matrix is the inverse of that matrix. And a sort of an iconic example of orthogonal matrices, just as a side note, are rotation matrices in sort of either 2 dimensions or 3 dimensions. If I take, I don't know, the surface of a sphere or something, and I take a vector on it, and I kind of rotate, those matrices are all orthogonal. Anyway, that was just a side remark. But these matrices are orthogonal, and the sort of middle matrix has the same dimension as the original matrix, and its form is also diagonal, but it's diagonal, but it's rectangular. So it's like it doesn't, like the diagonal values kind of don't go from the top left to bottom right. It's also padded with zeros everywhere else. For simplicity, I'm kind of assuming that there are more rows than columns here, and that is the case for most data sets. Typically, in data sets, we have some finite number of features, maybe 5, 10, 15, 20, perhaps. But we can have an arbitrary number of rows, right? Number of samples. So in the case of very large data sets, you can have millions of rows, maybe even billions, perhaps. And by convention, I will just arrange these singular values from greatest to least. Okay. So if so this kind of let's say that the rank of my original matrix is less than the total number of columns, then only the first sort of the first R singular values will be non-zero, and everything else will be 0. And that's actually also the case in regular Eigen decomposition. The number of sort of eigenvalues is the rank of your matrix. Number of non-zero eigenvalues, I should say. Yeah. Okay, so another way to write this SVD, we kind of wrote it in this matrix notation here as U, capital sigma, capital V transpose. Now, we can also write it in this kind of more explicit way in terms of the actual column. The UI and VI are respectively the columns of capital U and capital V. And so we can kind of write it like as a way where we take a column and a row, right? And we multiply column by row, etc. And we add all of those together. And these guys are kind of like actually will turn out to be building blocks for reconstructing a matrix. So that's actually this is actually where PCA gets SVD gets super cool, and I'll go into that in a few slides. So now the question is how I haven't really gone over how are these these sigmas, UVs and sigmas calculated, and the way that's done is so this X here is rectangular, and okay, I don't really know how to deal with rectangular matrices. Those are weird. I don't really like them. So I'm just gonna I'm just gonna make square matrices out of these rectangular matrices. And I like square matrices because I can compute eigenvalues and eigenvectors, and those are all well defined, and I'm happy. So I make square matrices out of those rectangular matrices, and then I just compute, do the standard eigen decomposition. And these singular values are the eigenvalues of both x transpose x and x transpose. And assuming that sort of the number of samples is greater than the number of features, which is the case in many examples. I would like to say most, but I hazard to say that because I could be wrong. But assuming that m is greater than n, then we can also have a large number of zero eigenvalues in this sort of first case. I have highlighted this second equation in blue because it'll come in handy and be important later. So I sort of mentioned these guys are building blocks here, and now let's talk about why that is the case. Well, actually, I'm not quite there yet, but we're getting there. Storing a large matrix can be computationally infeasible, especially if it's a really large matrix. So SVD, what it's really good for is approximating a large matrix. Because oftentimes all we care about is the approximate sort of answer, the approximate matrix itself. We don't really care about what it actually is. And more specifically, like when we say okay, but I could say okay, but there are a million ways to approximate a matrix. Like what exactly do you mean? And what I mean here is how do we give a rank k approximation where k is less than n, where n is the actual rank of the original matrix. Remember, this is an m by n matrix, so it has rank. It can have at most rank n. So how do we give a rank k approximation where k is less than n? And even more specifically, if we're given an m by n matrix with rank r less than n, where r can be less than or equal to n, what is the best rank k matrix B that approximates x for some k? Now, of course, I'm being vague here because, what do you mean by best? And to define best, you need some notion of distance, right? So if I could define a notion of distance, and I could take my original matrix X, and then I take B, which is the approximation, and let's assume that we just take some set, like the set of all rank k matrices, or set of all rank k m by n matrices. So in that case, we want to minimize the sort of by best here, I mean the one that is closest to x. And when I say close, the word close automatically implies a notion of distance. And so we need to define what closeness means, what distance means in this matrix space. And there are a couple of notions, actually many notions of distance, but these are kind of two big ones. One is sort of called the spectral norm, which is sort of this guy is kind of induced from regular Euclidean distance. And the other one is called the Frobenius norm. It's sort of written this way as a sort of square root of the sum of all the singular values. But it can also be written as You can just write it as the sort of, the Frobenius norm is just the sum of the square of all of the matrix elements, and then take the square root of that. And that you can show is equivalent to taking the sum of the square of the singular values and taking the square root. So these are two notions of distance. And either one kind of works. Actually, really, and there are others too, but these are just two examples of like defining distance. Okay, so now we have a notion of what closeness means. So what does that best matrix be? Well, there's a theorem that kind of gives us the answer to that. And it's sort of the answer to this optimization problem. At the end of the day, this is an optimization problem because we want to find that matrix B, that rank K matrix B that is closest to X. So turns out that the closest matrix to X is kind of what you'd expect. And by what you'd expect, I mean that because like basically I'm taking the entire singular value decomposition and I'm truncating it at K. And so I said building blocks earlier, right? So these guys here, these sigma 1, U1, so sigma I, U, I, V, I transpose, these guys are building blocks of the original matrix. And I can take some number of building blocks and I can truncate at whatever desired value K I want. And that is my approximation. So that is my rank K approximation to X. Okay, so I just want to give an example of this sort of matrix approximation. Let's say images can be represented by matrices. So color images have sort of 3 channels, the sort of red, green, blue channel, right? I think. Yeah. Anyway, 3 channels, and right. So those guys are actually tensors. They're not matrices because you have a sort of m by n, and then you have a depth as well. For simplicity of demonstration, I'll just restrict to a black and white image. So that's just kind of an m by n matrix where each matrix element is a pixel value, right, between 0 and 255. So let's say we want to store it like, I don't know, a JPEG image. Of course, like the JPEG compression algorithms these days are probably more complicated, but this is a very rudimentary image compression algorithm that actually works pretty well. Let's say that we want to store some m by n image where m and n could be large. And we want to sort of approximate this image with some rank K. We want to give a rank K approximation to this image, right, for some specified K. If we look at the equation here, this guy, these sigmas are sort of m by 1 matrices, and the V's are 1 by n matrices, right? And then we can just absorb into V because those are just scalars. So for each of these building blocks, we have to store m plus n values, right? And then we have to store that K times, right, for each building block. So that gives us K times n plus n, right? And generally, this number of values we have to store tends to be smaller than that one, right? And we can define a compression ratio to be the ratio of the compressed image, the number of values stored in the compressed image to the total number of values stored in the uncompressed image. And I just give an example. These are, since you guys are in Malaysia, I took an example of an iconic, photograph from Malaysia. And I kind of just ran it through this compression algorithm. And we can kind of see, as we get to like 0.2, even 0.1, we're getting pretty close to the original image. And the original image is back here. 0.8, and you can see like on the second row, like there's really not much of a visible difference between the various compression ratios. And so I can just store the compressed image on my computer and basically retain, most of what the original image was, at least visually speaking. And this thing here is called a Scalar plot. It's a plot of the singular values. That's the x-axis, and the y-axis. Or sorry, the x-axis is the sort of the like which singular value it is, sort of ordered from greatest to least. And the y-axis is the actual singular value. And you can kind of see that the first one is like huge, and then it drops like pretty dramatically. And so these two red dots here, this guy's 0.2 and this guy's 0.8. So, after, maybe the first, I don't know, 25 singular values or 30, maybe 40, like up till here, till about 30, like you're kind of capturing actual information about the image. But after that, it's like more or less a flat line. So you're not really getting anything out of it. And this sort of notion of projection is sort of like projecting this matrix, this large matrix, onto its first, by sort of reconstructing this matrix by its first k singular values, you're kind of maintaining most of the information, sort of capturing the salient information and sort of discarding the noise or higher order corrections, things that don't really have as much of an effect. So let's consider this image like a data set. We can reconstruct, as I said, the image from these building blocks of rank 1 matrices. And this sort of reconstruction of the data set or projection of the data set down to a lower dimension, this is exactly what PCA is to capture the salient information of a data set by projecting it onto the most important components. And said differently, PCA is just a statistical spin on the SVD, and we'll see this in a couple of. Well, actually, we'll see this like pretty much right now. So I'm just kind of bringing this back up just to remind you of the data that we're looking at. We have our samples, we have our features, and I call this X naught because I'll use X for what's called the mean subtracted matrix in a sec. So, given, the rows, so these guys, you can kind of treat these rows as random, as sort of, you can treat this as a random variable, as a bunch of random variables, actually. Each of these features are a random variable, and the rows are samples from that random variable. So the rows are from, 1 to m, where m is the number of samples, and k is sort of indexing over the features. And so we can define the sample mean, right, for each feature. So k is from 1 to n as just, the regular mean. And then we can also define the sort of sample covariance, just to give you some intuition for why this is what it is. Just recall, let's say we have two random variables, x and y. This x is not the same as the x before. I apologize for the abuse of the notation, but this is just some random variable. Then this is kind of the covariance. It's basically the deviation from the random variable from its mean. So we can kind of see that these are the respective means, and you take the mean of all of that. Right, and so this 1 over m minus 1 is the sort of mean over all samples. That's what this expectation value is. So it's a sample mean because we're taking the mean over these samples of this thing in brackets, and this thing in brackets here is the same as this thing here. So just a small side note. I put m minus 1 here instead of m, which is kind of what intuitively you'd expect. And 1 over m is also fine. This m minus 1, it's called the Bessel's correction. It's basically in statistics when you take a sample mean or sample variance, you can define this thing called an estimator, like a way how far, because this guy here, this QAB, this is an estimate of what's called the true covariance. And this also here is an estimate of the true mean, right? Because we're taking the mean from a sample, from a set of samples. And so an estimator is basically says, well, so these are the estimators, and the bias of an estimator is how far it is, like if the mean of the estimator is the true quantity, then that estimator is said to be unbiased. And in order for this covariance to be unbiased, an unbiased estimator of the true covariance, which we don't have access to and will never have access to, right? Because all we'll have access to are samples from the data set. And we can compute quantities from those samples, but we will never have access to what the true quantities are, right? But if we want an unbiased estimation, if we draw like these samples 100 times, 1,000 times, then hopefully we would want the mean of these estimators to be those true quantities, namely the true mean and the true covariance. And in order to get that that true covariance, you need to have this m-1 instead of m. And it's actually, you can read about it on Wikipedia. They have a derivation of why that's the case. So if you're curious about that, you can look that up. But anyway, that's the sample mean and the sample covariance. And I can kind of write this out. I've written this just in terms of matrix elements, but I can kind of rewrite it in terms of the original x. So I'm kind of defining x here. So remember I said x naught is our original data. And so the means are the means computed for each column, right? So this is the column 1 mean, column 2 mean, etc. So it's the mean of feature 1, the mean of feature 2, all the way to the mean of feature n. So the x is defined as the mean subtracted data set. So I take x and I subtract off the mean of each column from each column. So I take this column and I subtract off the mean of that column. Take the second column, subtract off the mean of the second column, etc., till the nth column. So that's what x is. And so this is these guys here. This is the mean subtraction. So we can kind of rewrite this equation in terms of our data matrix x. And remember that blue equation I flashed towards the beginning of this presentation. That was this guy right here. This x transpose x, in fact, is, well, it's up to that factor m-1, is the sample covariance. And the v, the right singular value, the right singular vectors of x are the vectors that diagonalize x transpose x. And sigma transpose sigma, which is an n by n matrix, because it's the matrix in the feature space. Those diagonal values, sigma 1 to sigma n, or the singular values of x, are the variances. And the eigenvectors corresponding to x transpose x. So the eigenvectors corresponding to x transpose x and the right singular vectors of x are the same thing. Those are the columns of v. And both of those are the principal components. Like the columns of v are the principal components of the data set. And I can project my matrix, my large matrix, onto these directions of largest variance to get from a high dimensional space to the low dimensional space. And the low dimensional space is spanned by the top k, where k is sort of the value you choose, principal components. That's exactly what I said. Cool. So I'm just going to give a simple example. Scikit-learn has a bunch of data sets you can play around with. You can kind of load it into pandas. And here's an example of a data matrix in the format that we've been looking at. We have our features, right? These are different features of the flowers, and we have samples. I've shown the top 5, but there are 150 samples in this data set. And each of these features, so this is kind of a feature vector. This is another feature vector, right? So these are all basically different flowers, right? And we want to say, well, what type of these three different flowers, I forgot what the actual colors, what the names are, but these three different flowers, do they cluster together, right? Do all the flowers from cluster of type 1 or type, there are three types in this data set, but do all the flowers of type 1, type 2, and type 3, do they kind of stay amongst each other, i.e., are these features good descriptors of those flowers, or are they just bad descriptors of those flowers? And they're okay descriptors. So what I've done here is I took the original data matrix X here, and I subtracted off the feature means, and I computed the SVD of it. So I have the U, sigma, and V. In this case, in NumPy, sigma, these are just the singular values. It doesn't actually give you the matrix in the same shape. It just gives you an array of the singular values. And then I kind of projected the original, or the recentered matrix onto the first two singular values, the top two singular values, corresponding to the highest variances, the directions of highest variance. And we see that kind of one guy out here, this flower is, different enough, but these two are pretty similar to each other. And so we can kind of see some amount of clustering, but it's not perfect. It's able to sort of distinguish one flower as very different from these two. So perhaps one hypothesis you might make is, well, maybe this flower is a completely different species. Maybe this is I don't know, I'm just throwing out names here, but maybe this is I don't know, a lotus, and these are, two different kinds of sunflowers or something like that. So, excuse me one sec. So that's kind of a way to distinguish between those two, those three different flowers. Okay, so that was PCA. Now we'll move on to LDA, linear discriminant analysis, which is a related dimensionality reduction technique, but it is supervised, unlike PCA, which is unsupervised. So in the case where you just have, so in this case, notice, I didn't actually make use, to do the PCA, I didn't actually make use of the label. Well, I did to draw these the different colors, but I didn't really make use of them really in any other significant way. PCA is a very good exploratory tool to understand the intrinsic structure of a data set. And in the case where you don't have labels, or you don't have access to labels, in this case, I had access and I was able to color those three classes. But maybe maybe I have a data set where I just have the data and I don't have labels, and maybe I might say as a hypothesis okay, well, I don't really know. I don't really know what types of flowers these are, but maybe this one I definitely know is pretty different from these guys here. These guys are similar to each other, similar enough to each other that I can't really distinguish them just from dimensionality reduction alone. But I kind of made some progress because I can at least separate out this one right here. So LDA is used for both classification and dimensionality reduction. In this talk, we'll focus on the dimensionality reduction aspect of LDA. Okay. So, all right. So let's move on to how it works. Let's say again, we kind of have start with some toy example. We have some data. We have two clusters of the data, the blue data and the red data. And clearly, we can kind of see visually that these are distinct from each other. And they should be clustered separately. They're different classes. Now, what's the optimal line to project this data onto? And by project, I mean take the data and kind of, put it, project it onto a particular line. So take the dot product of data with that line. So clearly, if I were to project this data onto this horizontal line, sorry, this 45-degree line here, then I would be kind of mixing the two classes, right? Because I wouldn't really, that would be a bad separator. But if I were to project on this line here, it would be a pretty good separator, because all the blue stuff would be projected down here on this side, and all the red stuff would be projected down here on that side. And they would be separate. So the question is, how do we choose this line? Like, what is the best line to choose? And so to do that, we'll be using what's called Fisher's linear discriminant analysis, which is sort of the way that Fisher approached setting up this problem. So let's say we have, we'll start with the simple case. Let's say we have two classes, and we have an embedded in some n-dimensional Euclidean space, and we'll define the respective means to be mu1 and mu2, where in mu2 we just replace xi by yi and n1 by n2. And then we define this mu tilde here, which is mu but projected onto V, where V here is the vector that optimally separates the classes. So we're trying to calculate, this is what we're solving for. Okay, and we do the same thing for mu2. All right, so to do that, we have to define some quantities. This sort of intuitive picture is to sort of optimize the ratio of the amount the two classes are away from each other to the sort of amount of variance within each class. And so S1 tilde squared, this guy here is really the sort of within class scattering. It measures the variability of the various data points from their mean. And this is just, we're just rewriting it as V transpose S1 V. And same thing for S2 tilde squared. Okay, so we're seeking to maximize this ratio here. This thing here is the numerator is just the means themselves. So we want these to be as far apart as possible, and we want to divide out the variation within each class, right? So we want to choose a V such that we sort of push we separate the centers of the two classes further apart compared to the variation within each class. Okay, and that's exactly what I said. Okay, so we can kind of rewrite this ratio in this way, where we define these matrices SB and SW. B is between and W is within, so it's between class and within class. So this is the thing we're trying to optimize. And this thing, so this optimization problem, so a lot of machine learning data science is like reducing a problem to a particular optimization problem. And oftentimes you'll find, like in the mathematics literature, a solution exists. So in the case earlier, when we were trying to find like the best rank K approximation, we sort of defined best in terms of a distance. And then we reduced that sort of notion of the best rank K approximation to some optimization problem in mathematics, and then that Eckart-Young-Mercy theorem gave us the answer. And so it's very similar here. We want to maximize this ratio. This turns out to be an optimization problem. This ratio is actually called the generalized Rayleigh quotient, and that is related to the generalized eigenvalue problem, which I thought of talking about here, but I decided not to put it on these slides. Anyway, so if you're interested, look up generalized Rayleigh quotient and/or generalized eigenvalue problem, and that's what this is here. And the sort of maximum value of this is the maximum generalized eigenvalue of this system here, and that's the corresponding eigenvector. Incidentally, this matrix SB only has is a rank 1 matrix, and so it's actually a lot easier to find to sort of work this out. It's a rank 1 because it's a sort of a rank 1. It's like a column times a row, which is the definition of a rank 1 matrix. Okay. So now I'll just briefly discuss the multi-class case, which is a generalization of the single class case. Notice we had this sort of between class and within class. In this case, it changes slightly, but the sort of general structure is there. We have instead of having the difference between the two means, we have a we have the sort of the means of the various classes, and we sort of subtract off the overall mean of all the data. So that's the between class. We kind of want we want all the classes to be as far away as possible from the total mean, and then the within class is just the same s's we defined earlier, but for each respective class. And again, that's the same generalized eigenvalue problem. And for k classes, we have k classes. I should have used a different letter actually. So I'm sorry about that. But for k classes, because I've used k like a million times. But anyway, for k classes, we want to find the top k minus 1 generalized eigenvectors. So this is the generalized eigenvector problem. So this optimization problem here is equivalent to finding the largest eigenvector that satisfies this system. So you can, if SSB is a square matrix, you can just kind of invert it, and then you want to find the largest eigenvector of did I get that backwards? Oops. SBV equals lambda s. I think I wrote that incorrectly because that doesn't look right. Give me a sec. I wrote this down like yesterday. No, that's right. Never mind. I just freaked out for no reason. Yeah. Okay. So I can just kind of move this to the other side, and then I say sorry, I meant to say SW inverse. I have to move the SW to the other side. That's why I just confused myself. So I move the SW to the other side. I say SW inverse SBV equals lambda V, and then we compute, and that's just a regular eigenvalue problem. And so the maximal eigenvalue, the eigenvector corresponding to the maximum eigenvalue is the thing that sort of separates things the most. And you can find the top k minus 1 of those. And so for k classes, we want to find k minus 1 generalized eigenvectors, and those are the class separators. And incidentally, it turns out that the rank for k classes, the rank turns out to be k minus 1. As in the case of 2 classes, the rank was 1. So that generalizes as well. So I just I want to take another example where I take a similar data set. I think these are wines. There are 3 different kinds of wines, and these are 13 features of like aspects of the wine. I'm no wine expert, so I don't know. These are like acidity and amount of magnesium and I don't know, color intensity, hue, etc., whatever. So anyway, we have 13 different characteristics of wine, and we have three different kinds of wine. And I think it's 3. And we're going to use both PCA and LDA to see how well we can kind of distinguish the wine classes. And in this case, LDA actually does significantly better than PCA. So PCA kind of, it doesn't know anything about the classes. And so all it does is it finds the directions of maximal variance and now I'm just projecting onto those 2 directions of maximal variance. In LDA, I'm trying to find those decision boundaries that sort of separate classes maximally. And so in this case, this dimensionality reduction technique actually turns out to be better than PCA. LDA turns out to be better than PCA because we actually know what the classes are. And utilizing, like making use of that, we can sort of separate the classes as far as possible and actually, make something out of it. So I think that is all I had. I think so. I just wanted to go over some points that were brought up in the beginning about pursuing a career in data science and machine learning. I think at its core, data science and machine learning is really it's very quantitative. It's very mathematical. Machine learning is very mathematical and statistical in nature. So having sort of a strong mathematics background in sort of linear algebra, like linear algebra is kind of the bread and butter of this entire talk. So knowing linear algebra very well will take you a long way. When I did physics, most of physics is basically linear algebra. Most of quantum mechanics is all linear algebra. So that's kind of how I got introduced to it. Statistics is actually something that I didn't really use as much in my research earlier. So it's something that I had to kind of pick up on my own later on. But if you can take a statistics class, I would highly recommend it, or maybe you already have, perhaps. And vector calculus is super good, useful for understanding how neural networks work. Because the way neural networks work is you have some it's like a bunch of matrix multiplications, a bunch of neurons, etc. They forward propagate, and you want to optimize some loss functions. You want to back propagate through that whole thing using single gradient descent, and that's all vector calculus. So those three math topics, really, I'd say know pretty well. On top of that, programming, just get comfortable with Python. Things like the things I use in this talk, these packages here are good to tinker around with small data sets, like in this presentation. But for large data sets, at work, I deal with very large data sets, and data sets that can't be all stored in one place. So they have to be stored in this distributed fashion. Spark and PySpark is the sort of Python interface with Spark is really kind of used for analyzing and applying machine learning and data science to data sets at large scales. So Spark is something that's very helpful and very, very important, I would say. And actually, something it just came to mind now. I didn't put it on here, but also SQL is super important, because typically most of the time, the data itself isn't, in this case, the data was kind of just given to us cleanly. It's like, hey, here's the data set, now you can play with it. In most real world applications, the data is not just readily available. You have to query it in some large database, and usually the way you query it is via SQL. So knowing SQL is probably good as well. Although that's something I learned, once I started my job. So SQL and Spark are things maybe you might not need to know going in, but certainly once you do start any job in this space, you will be using both of those very extensively. Now, if you're interested in going to deep learning, I didn't talk about deep learning in this talk, but there are two competing frameworks, TensorFlow and PyTorch, for playing around with neural networks. So that's certainly something to explore. There's a lot of really good documentation on it, on both of them online. And you can find tutorials and stuff like that. I personally prefer PyTorch. I had done some stuff with PyTorch in grad school, just playing around, and I liked it better. It was better structured. So that's my personal preference, but TensorFlow is good too. So yeah. Anyway, reach out on email via email or LinkedIn if you have any questions. But otherwise, thank you.
So thanks, Divyanshu, for the talk.
Yeah.
We have a question right now. Let me just share it here. So,
why would you do PC? What would you do in PCA to get the same projection as in SVD? Let me go back. So if I understand your question properly, So PCA and SVD are slightly different. So the sort of notion of projection comes from PCA because you're projecting onto the sort of largest principal components. Perhaps I should have made that more clear. But in SVD, you're kind of reconstructing a matrix from building blocks. So PCA and SVD are related, but not exactly the same. PCA is kind of built on top of SVD.
All right. I guess that's about it. So thanks again for joining us today and giving us this talk. I hope that our viewers enjoyed it. We've been getting a lot of hearts and likes from our community. So to our viewers, thanks again for joining us as well. So before we end, I just want to share about the application for the Developer Student Club leads. We've been talking about this for a month now, and like we mentioned last week, the application has been extended now. So for those of you who would like to be a DSC lead, take this opportunity. This is your time to try out something new and connect with experts from the industry, and also improve your knowledge as developers. So that's about it. Thank you. Divyanshu, do you have anything to share before we end the live stream?
I don't think so. No. Yeah. No. I think.
All right then. So thanks a lot, everyone.
Great.
Developer student clubs train thousands of student developers globally and work with their communities to solve real-life problems. Google selects amazing students from across the globe once a year to be a developer student club lead and start a club on their campus. These leads believe knowledge is power and that technology can do extraordinary things for the world. They take on the responsibility to help students learn and empower these students to solve real problems around them. Join us in building a global community for students.